We're going to talk a little bit in detail now about reflection. We have reflection when we have a wave propagating in one media, let's call this medium 1, and it's incident to what we call medium 2. Medium 1 is characterized by its dielectric permittivity and magnetic permeability, and medium 2 also by its constituent parameters. Now notice that this is the usual case in which you have an antenna propagating we have an antenna, and we always have the ground that has a different dielectric properties than the atmosphere. So we know that when we have the incident wave, there will be on one hand a reflected wave, and then we'll have a transmitted wave. We know that because of Snell's law of reflection, that reflecting angle is equal to the incident angle, and then that transmission angle is related with the incident angle with Snell's law of refraction. Now, we'll define what we call the Fresnel reflection and transmission coefficient as certain coefficients that relate the reflected field with the incident field and the transmitted field with the incident field. And those reflection coefficients actually relate those fields at the interface. So actually I have an incident field, and the reflection Fresnel coefficient, actually what it tells me is, it relates me the reflected field at the interface related to the incident field at the interface. There are some special interesting angles. One is the angle for which we have total transmission. That means that the reflection coefficient is 0. So if I have an incident field, there is no reflection and all the field is transmitted. And when this happens, this is called the Brewster angle. And then another interesting angle is what we call the total reflection. That means that when I have an incident field, the reflection coefficient is 1. So all the incident field is reflected. This is called the critical angle, and we can see from that characteristic, from that expression here, that this is the expression of that critical angle. Now, this is the basic geometry. Now let's study a little bit more in detail. When we talk about the Fresnel coefficients, there are two different cases, depending on the polarization of the electric field. Now, in this first situation, related to this picture, this is what usually known as parallel electric field, TM wave, or vertical polarization. Now, let's see why we use these names. The first thing is that when we talk about the incident plane, you have to imagine that the incident plane actually is the plane of the screen. Okay? So, in that case, the electric field is contained in the incident plane. So, this is what it's called, we call this situation parallel electric field. Also, the magnetic field is perpendicular to the incident plane. So this is what we call TM wave. It's a TM wave, that is the magnetic field, which is this one, perpendicular to the incident field. And if you think a situation that we are trying here to represent an antenna, and this is the ground, well, that electric field is essentially vertical. So this is what we call also this situation vertical polarization. Well, given the situation and the representation of the incident and the reflected field, and using the boundary conditions at the interface, and you know that the boundary condition in the interface is that the tangential component of the electric field has to be continuous, we can find the reflection coefficient and the transmission coefficient. Okay? And those are the expressions that depend on the incident angle, transmission angle, and also depend on the values of the characteristic impedance of the medium 1 and the medium 2. The other case is what we call perpendicular electric field, TA wave of horizontal polarization. Notice that in this case, the electric field is perpendicular to the incident plane. This is why we also call this the TA wave case. And also, if you imagine that this is the ground, in that case, the polarization is horizontal. So this is why we call also that case horizontal polarization. Well, we can derive the expressions of the reflection and transmission coefficients are these ones that you can see that they're slightly different as the one we had before. Now, what is the implication of that when we consider wave propagation? Well, let's consider what could be a realistic case in which we have the atmosphere. We're going to assume that the dielectric constant and the relative dielectric constant and the relative permeability is 1. Let's consider the case of what we call moderate dry soil. That is a soil that has a dielectric permittivity of 15 and a conductivity of 10 to the minus 3 Siemens per meter. And in that case, we can use the previous expressions to find the magnitude and phase of the reflection coefficients. This is the magnitude and phase for perpendicular horizontal polarization and magnitude and phase for vertical polarization. And we have here for 3 different frequencies. 1 megahertz, 4 megahertz, 12 and 100 megahertz. Notice that except for the case of 1 megahertz, all the other cases are almost the same. Now, what is the important thing here? Well, the important thing here is to realize that for this angle theta close to 90 degrees, and notice that when we go to 90 degrees means that our angle of incidence is increasing, okay, and it's close to 90 degrees. Notice that the magnitude in that case of the reflection coefficient is close to 1, and the phase is close to minus 180 degrees. So in that case, the reflection coefficient is approximately minus 1. And in this case, for vertical polarization, the magnitude of the reflection coefficient is close to 1, and the phase of the reflection coefficient is close to 0. So in that case, the reflection coefficient for vertical polarization is close to 1. If we go to wet soil, in that case, wet soil has different electric properties. The conductivity is larger and also the electric constant is larger. Well, we can compute the Fresnel reflection coefficients, and well, they are different. But the important thing is that also, once again, for an incident angle close to 90 degrees, for horizontal polarization, which is that case, the reflection coefficient is close to minus 1, and for vertical polarization, which is this case, the reflection coefficient is close to 1. Okay, so let's see what happens now when we have a transmitting antenna and a receiving antenna. And of course, they have to be over the ground. So, well, we'll have a direct path with a distance d1, and then we'll have a reflection on the ground. That wave will travel a different distance, d2, and there will be a reflection on the ground, and of course, that wave will be reflected according to our reflection coefficient. Now, here at the receiver, we'll have the combination, if you want interference, of this wave, the direct path, and the reflected wave. And of course, depending if they are in phase or in opposite phase, I will have a constructive or a destructive interference. Notice also that for most of the situations, if this distance is large compared to the antenna height, the incidence angle, remember that we measure the incident angle according to the vertical, is close to 90 degrees. So in that case, we can approximate the reflection coefficients either as minus 1 for horizontal polarization or 1 for vertical polarization. So let's see the result of this two-wave propagation model. This is just applying the model for a frequency of actually 2.1 gigahertz. We are considering isotropic antennas. That means that if we are considering isotropic antennas, it means that this antenna is radiating isotropically. So actually what is radiating in this direction is the same that is radiating in this direction. And also the receiving antenna is isotropic. So the antenna receives the same for a wave coming in this direction than a wave coming from this direction. We are assuming a flat Earth. We are assuming that the distance between antennas is much larger than the antenna height. So that means that we are approximating the reflection coefficients either for 1 or minus 1. And well, those are the antenna heights that we are considering. So we are plotting the transmitter-receiver distance. This is the log scale in meters, and this is the isotropic path loss. The blue line is free space, and then we have two cases, horizontal polarization and vertical polarization. Okay, we can see that when we have a constructive interference, that point here, that is that the incident wave, the direct path and the reflected path ray are in phase, of course the field increments by a factor of 2, that means a gain of 6 dBs. So in that case we have 6 dBs more than what it would be expected from free space propagation conditions. But when they reach the antenna, the reflected ray reach the antenna in opposite phase, we have a destructive interference and then we have a null. So actually those maximum minima that we are having is because we either have constructive or destructive interference. Of course, this is a flat Earth model, so actually it doesn't make sense to extend it to very large distances because we have the horizon. Okay. But in any case, it's also important to notice that for large distances we have two different behaviors when we consider the polarization. For vertical polarization, we have this sort of behavior in which we gain 6 dBs more compared to free space propagation, while for horizontal polarization we have this behavior in which we see that the attenuation as a function of the distance actually has a much higher slope than we will have in free space, considering just free space propagation. If we look a little bit more in more detail, here we're plotting the case for horizontal polarization, that is considering a reflection coefficient of -1 for two different frequencies, 900 MHz and 180 MHz. The dotted lines are free space propagation. Of course, if we double the frequency, or we change the frequency by a factor of 2, we have a 6 dBs difference. Here we can observe in each one of the frequencies how, well, depending if we have constructive or destructive interference of maximum minimum. But the interesting thing is to see that that slope actually, or that behavior here, is the same independent of the frequency. It doesn't depend on the frequency. And that slope, instead of depending as 1 over r squared, depends as 1 over r to the 4th power. So actually, for horizontal polarization, the ground reflection actually puts a heavy penalty on the propagation at long distances. When we consider the vertical polarization, we see that in that case, the behavior depends on the frequency, and in the limit, we always obtain 6 dBs more when we consider ground reflection than we would obtain just considering free space propagation conditions. Now, up to what point this two-ray model is exact? Well, probably the largest thing that deviates from reality is that in most applications we use directive antennas. That is, that the antenna has a certain radiation pattern. For instance, something like this. This is the radiation pattern corresponding to a uniform array with 8 line of length and with a certain tilt angle. So the antenna is not pointing to the horizon, but it's pointing downwards a little bit. And what that means is that they have this sort of antenna. Well, the radiation of the antenna towards the ground, okay, is much smaller than towards the receiving antenna. So in practice, the situation is a little bit different. So here what I'm plotting is for that previous antenna, the field intensity, if you want the free space propagation losses that we have once we consider the antenna radiation in a vertical plane. This is the distance, and we are assuming that the antenna is at a height of 50 meters. And here what I'm plotting is the received signal if someone is moving with an isotropic antenna at 2 meters above the ground. So actually what we see is that, well, that isotropic path loss has a very different way, or a very different shape from what we would expect. Because essentially you can see that in this area here, I have so many little lobes of the antenna, so I have this sort of situation here. Here I'm moving around the main lobe, so this is those sort of situation. And of course, I have a decay on the received signal, but that decay is due two elements. One, because I'm moving farther away, but also because the antenna has a certain radiation pattern. Now, if I consider what happens when I have reflection on a wet soil, I obtain something like this, and this is the plot, the same plot of the losses that I would have if I move 2 meters above the ground. And notice that, of course, I have a certain distortion, but I don't see now those nulls that I was seeing before when I was using isotropic antennas. Why? Well, I can see that in this place here, probably there is a cancellation from the direct and the reflected ray, but of course, the reflected ray is radiated at a lower level, so it's not able to cancel the direct ray. There is a certain reduction, but not a clear cancellation. Also, we are considering that reflection is occurring in a perfectly smooth surface, but usually what we have is we're going to encounter in real situations are rough surfaces. So in those cases, more than reflection, we'll talk about scattering. Of course, when we have a very smooth surface and I have an incident ray, essentially all the energy is reflected assuming Snell's reflection angle. So all the energy is concentrated in this direction. But when I have a rough surface, actually what happens is the energy is scattered in many directions. And of course, when I have a very rough surface, the scattering becomes very diffuse. Actually, I'm scattering that energy in many directions. Usually, there is what is known as a Rayleigh criterion that tell us when I can consider that I have reflection or scattering. And the idea is the following. I have a rough surface here, and I have an incident ray, and I have a reflected ray. And if I assume that the distance, that distance ABC, compared to the distance EFG is smaller than a quarter wavelength, I can assume that this is a smooth surface, but if that difference is larger than a quarter wavelength, then I'm assuming that we have a rough surface. So if we put the equations, we can see that this is the criterion, and of course usually H is taken as the root mean square value of the surface roughness. So if we put certain numbers, we can see that at 1 gigahertz, in which the wavelength is 30 centimeters, we can see that that criteria is talking about a roughness of about a few centimeters, at 10 gigahertz of less than 1 centimeter, and of course at visible light is less than 0.09 millimeters. So actually, in most of our situations, we don't have a clear reflection, but we should be talking more about scattering. And to have a clear image of what scattering is, we have this picture here, in which you have the sun, it's either a sunset or sunrise over the ocean. And notice that we don't have a clear reflection. We don't see an image of the sun, but rather we see this thing here, which actually is the scattering. What is happening is that the ray lights that are hitting the ocean actually become scattered. So we see light coming from here, from here, from here, from here, because scattering is occurring. So reflection, well, ground reflection is almost inevitable in terrestrial radio communication. We can consider a simple two-ray model to understand what is going on. Actually, what the two-ray model is showing that we have a reflection, we can have either constructive or destructive interference. The fact is that if we use directive antennas, the effects are less severe than it would be essentially predicted using that isotropic antenna model. But also, we have to take into account that for most of the cases, situations we will encounter, we don't have perfect reflection, but we have more than scattering phenomena, which is a little bit more difficult to take into account, and actually will also reduce those interfering effects, those cancelling effects of reflection.